In this challenge, you're given a list of words written in an alien language, where the words are sorted lexicographically by the rules of this language. Surprisingly, the aliens also use English lowercase letters, but possibly in a different order. Given a list of words written in the alien language, you have to return a string of unique letters sorted in the lexicographical order of the alien language as derived from the list of words. If there's no solution, that is no valid lexicographical ordering, you can return an empty string. Now, the lexicographic order of a given language is defined by the order in which the letters of its alphabet appear. In English, the letter N appears before the letter R in the alphabet. As a result, in two words that are the same up to the point where one features N and the other features R, the former is considered the lexicographically smaller word of the two. For this reason, ban is considered lexicographically smaller than bar. Similarly, if an input contains words followed by their prefix, such as educated and then educate, these cases will never result in a valid alphabet because in a valid alphabet, prefixes are always first. Okay, and here are some examples. If you have BA, 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 what does that tell us? It tells us that the letters are AB work, right? I think AB or even BA, those are two valid arrangement of characters we can deduce from this. Then here we have this sequence of letters. It's like A, B, C, D, E, but in the alien language, right? So that this is what it comes down to. Same with these, and it's kind of be a bit hard to follow. But the fact that X is here and then P tells us that X comes before P in their alphabet, as you can see in this ordering, right? And then in this case, there's nothing tells us how it works in this case, and that's why it's empty. And you're going to see how via the solution. Let's look at the solution, the explanation for this. It's quite a lot, but again, if you follow the pattern that we're dealing with right now, like the topo sort pattern, we're gonna use that to figure things out. I think reading these is useful, so let's get to it. So we can use the topo sort pattern, which is the sequence of videos we're exploring in the next few days, and it's used to find the linear ordering of elements that have dependencies or priority on or priority over each other. So if A is dependent on B or B has a priority over A, then B is listed before A in topological order. So using the array of words, we identify the relative precedence, order of letters and words, and generate a graph to represent this order. To traverse a graph, we can use breadth first search to find the letters order. Okay, so we take the array of words that they give us, right, and we identify the relative precedence, order of letters in the words, and generate a graph to represent the ordering. And then to traverse the graph, we can use breadth first search to find the letters order. So we can map this to a graph problem, but before exploring the exact details, here are a few things to keep in mind. The letters within a word don't tell us anything about the relative order. So in the word educative, in the array, it doesn't tell us that E is before the letter D because it's within a single word. Okay, and then the input can contain words followed by their prefix, okay, such as educated and then educate. Now, these cases will never result in a valid alphabet because in a valid alphabet, prefixes are always first. So educate should always come before educated. But if the order is switched, then we can't deduce a valid alphabet sequence of characters because an empty string is empty character is before the letter D in this case. So we need to make sure our solution detects these cases correctly. And there can be more than one valid alphabet ordering. It's fine for our algorithm to return any one of them, just like if you remember in the beginning, the A, B, B, A, B, A, B, A, you could have been A, B, or B, A. Either one would have worked. Now, the output dictionary must contain all unique characters within the word array, including those that could be in any position within the ordering. It shouldn't contain any additional characters that weren't in the input. So these four things are super important. And now we're going to build the solution gradually, or we can skip straight to the code. Let's see what they have to say about this. Let's follow along. Now for the problem, we can break it down into three parts. So we extract the necessary information to identify the dependency rules from the words. For example, in the words patterns and interview, the letter P comes before I. We know that for sure because this came before this. And now with the guided information, we can put these dependency rules into a directed graph with the letters as nodes and the dependencies as the edges. Okay. Lastly, we can sort the graph nodes topologically to generate the letter ordering. That is the dictionary that we're looking for. Let's look at each part in depth. Okay, so we're identifying dependencies first of all, right? First of all, we identify dependencies. Next, we put them into a graph. And lastly, we sort it with toposort, the graph with toposort. So imagine we had all these words. Okay, and this is their ordering, right? And they are sorted lexicographically, so alphabetically, right? And now, we know that this is basically saying that the first characters are sorted alphabetically. So we have these from this, and then we're going to remove the duplicates and we'll wind up with this, which is very useful. And so now this diagram shows the same thing, the long sequence of words, the first character of each of the words, then removing the duplicates of all the characters. Now, we know the relative order of the letters, but we don't know how the letters fit in with the rest of the letters, okay? So because of base, we only dealt with the first character of each word. Now, to get more information, we need to look further into the English dictionary analogy. The word dirt comes before dorm, and this is because we look at the second letter when the first is the same. So in this case, I comes before O in the alphabet, right? DI versus DO. And now we can apply the same logic to our alien words and look at the first two words, MZSOR and MQOV. As the first letter is the same in both words, we look at the second letter, and the first word has Z, and the second one has Q. Therefore, we can safely say that Z comes before Q in this alien language. We now have two fragments of the letter order. So if we're comparing each word by the one beside it, you notice that this is the same, like diagonally, right? It tells us that Z comes before Q, right? M comes before X. X and X are the same, but X and A are here. So X comes before A, X, A, and Z, X, A, and Z, but V and A are here. So V comes before A, and so on, right? So this is, we're generating the dependencies. And I believe that was still in step one, where we're generating the dependencies. And we're not dealing with secondary dependencies because we can derive them this way, right? For now, we're only doing direct dependencies in this ordering. And now this is the first part. And then the second part, we need to represent the dependencies. So we have a set of relations for the relative order of the pairs of letters, okay? So we have this, we've drawn this out. Now the question arises, how can we put these relations together? You might want to chain them, which is tempting, as they say here, but some letters might appear in more than one chain. Putting the chains into the alphabet array one after the other won't work. Some of the letters might be duplicated and some result in an invalid ordering. So let's try and visualize the relations better with the help of a graph. The nodes are the letters, and the edges between two letters, X and Y, represent that X before Y in the alien words. So we have this graph here, and it represents this. Everything here can be represented visually this way. And now we want to generate a dictionary, and I think it's useful to move back and forth between this and what comes next. So as you can see from the graph, 4 of the letters have no incoming arrows, and the ones in green have no incoming arrows. And that means there are no letters that have come before any of these 4. Okay? So there can be multiple valid dictionaries, and if there are, then it's fine for us to return any one of them. And so in one case, we can just have this ordering. So just take OMUZ, and it could come in any pattern, right? It can be MZU, OMUZ, OZ, OM, OZUM, etc. Okay. So then toposort, if you follow the last video, right, this is the pattern, right? This is where you can notice the similarity between them. We can remove them from the graph. So we take these from the graph, and we'll wind up with these. Now these have nothing coming into them, X, Q, and W. So there are now 3 letters that have no arrows in, and we add what we just took out. I mean, these new 3 letters right into our output array, then remove again systematically. From removing these, we then remove V and S, and then we remove A and R. And then this is a valid ordering. So how would we do this in code? we can use an adjacency list, right, as you see here, to represent the graph. So this represents the graph, right? These are, imagine these are keys. The first row is keys, and the second row is values, right, which are an array of the children. Next, we get a dictionary from the extractor relations. And then we identify the sources, that is nodes with no incoming links, and identify whether a particular letter has any incoming links or not from our adjacency list. And doing that can be a bit complicated, actually, is what you're trying to say here. How they figure it out, though, one alternative is to have two adjacency lists, but what they do at the end of the day is just keep track of the in degree. So basically this says for every node here, how many edges are coming into the node, right? So the sources have nothing coming into them, while everything else has a number of an integer number above 0. And so every time we take a source that is a node with no incoming edge, we decrement the in degree, right, instead of removing it from the adjacency list, and that makes things easier to manage. And if you remember, follow the last video, we did a similar thing. We took a similar strategy. So that's how these videos are similar to each other. And when it reaches 0, the node has no incoming sinks left, and we use a breadth first search on all letters that are reachable. That is, the in degree count of the letters is 0. A letter is only reachable once the letters that need to be before it have been added to the output result. And we're going to use a queue to keep track of the reachable nodes, perform breadth first search on them. Initially, we put letters that have 0 in degree count, and then we keep adding letters to the queue as their in degree counts become 0. Okay, we continue until the queue is empty. Next, we check whether all the letters in the words have been added to the output or not. This would happen when some letters still have some incoming edges left, which means there is a cycle. In this case, return an empty string because it means there's no valid ordering. And there can be letters that do not have incoming edges, and this can result in different orderings for the same set of words, and that's all right. So then we visualize the algorithm, but before we do, I think I'd like to even look at the code at this point. I think now is a good time to look at the code. And what does the code look like? Okay, so we have this function to give us a function to pass in the words, and then we create the adjacency list. With this fancy thing in TypeScript, the definition is in the code in the GitHub repo for this default dict. It's a custom data structure, and I'd like to show the explanation real quick. So this is the implementation, right? I asked the AI to explain it to me, so it gives this explanation. You feel free to pause the video, right, and study this this explanation that the AI gives. Okay, it's useful, but again, not what we are dealing with precisely. And so when we hone in on this function that we're describing, right, we use counts to store the number of unique letters. So we look through the words, this is a standard pattern, and then for each word, right, we set its frequency. It's like a frequency map to 0, each character in each word. So we initialize it to 0. So counts, the keys of counts represent the unique characters in the array of words. Okay. Next, we populate adjacency lists and counts, and then for each. The next block of code, this comment is useful, but it compares the two words side by side, and I think this diagram, this comparison here, happens with within this call here. Zip does something to two words, right? It helps pair them up the way we have them paired up here. Earlier, you can see the implementation here is fairly straightforward based on the length of the first array you pass in. And then this is like moving it in character by character, right, for each word. And so we loop through that, and then we get the first character from word 1, the second character from word 2, right, and we zip them again, and then we loop through T. Okay, so we get the first character, for both words, I believe, yeah. And we compare them. If they are not the same, right, then we add it to the adjacency list, increase the count over here. So because it's a child of D, right? They're increasing the in degree, right? And then if it's not broken, right? If they are one is a prefix of the other, then just exit. So there's a lot going on here. This is why it's a hard problem, right? And then if we should exit, right, then just return null. And I think at this point we're here, right? So we've created our adjacency list. We have our in degree counts, which represent as counts. We have a queue. Okay, we haven't gotten to the queue. So we have the queue here. And we have the results. And now for every character in counts, we pick everything that has a source. So the in degree is 0, we enqueue. As you can see, that's why we have ZUMO here. Everything that has 0, we enqueue, we add to the queue over here. All right. And then while the queue, there's stuff in the queue, we dequeue. First thing, we put it into the results, then we check all of its children, decrement their in degrees, right? And then if any of the children have an in degree of 0, they become sources, then we enqueue them. Okay, that's what we're doing here, and that's the whole flow here. All right. Took Z out of the queue over here. Because we did that, all its children, we decrement their in degrees. So you notice these Q and X here. All right, we decrement them, and because this became 0, we added it to the queue, just like in the code here. And then we loop through that way and populate results, right, by looping through the queue this way. And we just do that all the way, that whole process. Okay. And we just keep doing that. Okay. Now it's like watching a recipe, right, for like a cook. If someone was cooking and you're just following a recipe, after a while you get the intuition for why we're doing everything we're doing, but you have to know the steps and follow them in the right order. So finally, right, we check for cycles. That's this check right here. They don't match, the counts don't match, it was a cycle, so just return nothing, otherwise just join them and send it out. And the time complexity is as complicated as the solution, right? But you can pause and look through the explanation they have here, which is a lot, but at the end of the day, right, we get a time complexity of O of C, right, where C is, I believe, the number of unique characters in the total number of letters C. Okay, and space complexity based on the fact that we're dealing with the maximum alphabets 26, similar to, we've seen this before. We have O of 1. So yeah, that's all there is to this problem. 20 minutes long. Oh, so much going on. But see you next time. Cheers.